Welcome back to the HVAC-Engineering-Techie channel. This is a channel where we talk all things HVAC. We talk about engineering design, construction, equipment, systems, test and balance extensively, controls, and efficiency and system performance. Today, our lesson is on tab air balance and constant volume systems. Now, this is T-14 in our series of lessons. And this is the first one that actually is going to talk about how balancing a system. All the ones before about taking readings or something specific about balance that you need to know as background. This is the first one we're going to talk about systems. So this is a little longer video than most because we're going to do all the constant volume systems, which is several systems. And I think you'll find this interesting. You may have to watch this one a couple of times to be able to figure out everything we're talking about here. This is how you basically balance the constant volume systems. So appreciate you being here today. I appreciate you being a subscriber. If you're not a subscriber, would you mind becoming a subscriber to the channel? It's free, it costs you nothing, it's painless for you, and it really helps me because Google uses that data to evaluate this channel. So I'd appreciate it if you click the button down below. That would give me a thumbs up. That's really helpful. And let's start talking about air balancing constant volume systems. First of all, we need to do some preliminary things before we get to the site to be able to do an effective job. You don't want to wait to get to the job to look at the drawings. You want to make sure you fully understand what you're doing here. So to fully understand how to balance a system, you must do a design review. And you're looking at this as a design review for tab. So what you do is you do all devices, including supply, return, and exhaust grills, to indicate size, flow, and throw. So that's what you need to know to be able to balance the job. So is it shown on the drawing? If it's not, you're going to have to ask the design engineer, I need to know what flow this particular grill has, what size, what flow, and is it a four-way? If the drawing doesn't indicate it's a four-way throw or three-way throw or two-way throw, you need to know that information. Do flows of components match? That's important. Do the supply fan and coil and filter CFM, do those all match? So the supply fan, does it match the CFM of the coil? Does it match the CFM of the filters? Because if not, it's not that you're going to balance the different ones, but you need to make sure there's not been a design error somewhere and the coil now has too high a flow. Like chill water coil should be under 500 feet per minute. And if you have a chill water coil with 600 feet per minute, it'll blow the water off the coil. Now you're going to have a problem. So you need to figure those out ahead of time. Return fan CFM plus outside air CFM equals the supply fan, to make sure that's going to work, because if not, then the return fan CFM has to be less. So so those need to add up. Total flow of all connected grills and terminal boxes match supply fan CFM. In a constant volume system, there should be no diversity. Now, in a VAV, it's possible to have more CFM at the box level, at the zone level, than it is at the main level. But for constant volume, it is not, because it doesn't vary. So for a constant volume system, everything needs to add up. Now, you say, well, how could you have terminal boxes? Well, you may have reheat boxes or something like that. Some terminal boxes that's not variable flow, it's constant flow. So you need to make sure that you have no diversity in those. And the only reason you'd ever have diversity has been a mistake. And then you need to work on that mistake. Review design for system effects issues such as broken back elbows, sharp transitions, or increase in duct velocity. Normally velocity gets lower the further it is from the fan. So system effect is actually requiring more horsepower as you go down the duct. So here's the thing. As a fan pushes air to start the velocity down the duct, that should be the highest pressure it sees. And as it goes down the duct, the pressure decreases because of friction on the duct. If you have an instance where you're going along with a velocity of 1,200 feet per minute and all of a sudden they have a smaller duct, it goes to 1,400 feet per minute, that's system effect. The reason is because that increase is going to require more horsepower. So it shouldn't be. That velocity should always be getting less and less and less and not more. So that's a typical thing, and the broken back fan just means that there's some things happening in the fan that's going to increase pressure a lot. And so we don't want that. Poor fittings that are not designed correctly will induce a lot of pressure, and that it's a problem for us. And the reason the balance guys are concerned, that's an energy deal, right? Because to get flow, you may have to start jacking that fan up past its capacity because the engineer really didn't count on that pressure increase. So we need to make sure we understand if there are areas of concern, so we'll know what to do and look at it in the field. Special access areas are reviewed, such as slope floors, very high ceilings, or obstructions to access. To be able to balance the job, you got to get to it. So you got to make sure you don't have some conditions. You're going to have special scaffolds or lifts, and you need to know that to be able to do your job. So now you need to do a field review before you start to balance. So you need to go to the site, walk the system, and you need to look for these things. Air distribution systems are complete with all air handling units, ductwork, terminal units, grills, diffusers, and dampers are installed per the design. So you've got them there. It's really irritating when at the office you've done a layout and you got your forms all created and you go there and it don't look like it did on the drawing. So all of a sudden they got more grills or less grills. Now you're messed up. You got to figure out what's going on. Now you can change your forms and everything, but why was the change made? Was there an addendum issued on the design? If not, why did the contractor change it? This may not be a desirable. It may need a phone call and a discussion to figure out if this is acceptable with everybody that's changed. Volume and smoke and fire dampers are 100% open. Now you're going to get tired of hearing that. I know you're going to get tired of hearing that because we talk about it on every single system, but it is the number one thing you have to do to actually balance the system correctly. Clean filters is another thing you get tired of hearing about, but you can. I've seen sometimes this is a subject I don't talk much about in here, but sometimes the specifications call for you to balance a job with a certain pressure drop across the filters. They're trying to simulate dirty filters instead of clean filters. Normally my advice and of everything I talk about is make sure we have clean filters before we balance so we can get maximum flow to do the balance. And if you have to simulate flow, what you have to do is put pieces of cardboard in some of the filters to act like a dirty filter so we increase the pressure. And you can do that to get flow, but it's really best to do clean filters so you can get maximum flow, especially on systems that are somewhat limited. Fans have been started up and operating, free from vibration and rotating in the correct direction. Very important. You might as well just do this right up front and not have to worry about it when you get there. Because if you got a fan that's vibrating, you could damage the fan by keeping it operational. So you should notify the mechanical contractor and say this fan needs to be balanced. It's got a problem. Dynamically balanced, so it stops vibrating. Variable frequency drives have been started up and programmed, and they're ready to go. Automatic temperature controls are installed, programmed, and operational. Now, I know that this may not always happen. They need you to balance the job, and the control guy's not done. Well, that's fine, but you must be able to change valves, damper positions, start and stop equipment. You must be able to do that through the controls. If not, then it's not ready for you to balance. Control software for operating and calibrating controls has been received from the control contractor and its operational training provided to you. So you have to make sure you know how to calibrate a VAV box and you have the right tools to do it. You can't do your job without it. So the next thing is HVAC system is started up and temperature control is being provided to the space. The ceilings are installed. Building enclosures are complete with windows and doors installed. You can't balance a building for final pressure if it's not done. I mean, the building has to be enclosed, ready, not total ready for occupancy, but it's still, we don't care about paint, we don't care about floor covering, we don't care about that, but we care about ceilings, we care about everything that is involved in pressure differential for us. So that needs to be done. I mean, it sounds weird, but we've had general contractors try to get into balanced buildings that don't have any windows. We just can't do it. Well, you could go in and balance maybe some grills, but you should not, because you're going to have to remobilize to finish it once they do. And mobilization will kill you on productivity. So you need to say, no, when you're done, we will come and do the job. And you have suitable access to be able to get to everything you need. They don't have, I've done jobs that have secure areas you can't get in. So, you have to have someone with you. You have to have some way to get in that secure facility to be able to balance the jobs. And they will do that because they have to have it balanced, but you may not just be able to walk in by yourself. Okay, the first thing we're going to look like is a heating ventilating unit. So how do you balance a heating and ventilating unit? So a heating ventilating unit, of course, is just a hot water coil or a gas furnace and a blower that heats a space, normally a warehouse or something like that. So this one is a hot water coil, so it has a hot water coil, and it has a control system, and the control system is basically just a room thermostat that modulates this valve or open and closes the valve to heat. The rest of this could be a start-stop for a system. So now when we go through talk about systems, I'm going to do a really short sequence review, just because I think to be able to balance the job, you need to know what it's supposed to do. And so basically it's just really easy. The fan's on anytime the building's occupied, and it opens and closes the control valve to maintain the temperature. Super. No big critical deal there. For balance, now, you notice I had a little bitty box for this control. We have a great big box for balance because we have things to do. Guess what number one is? Verify all grills are 100% open. You're going to get really tired. And I won't spend a lot of time on these redundant ones, but verify clean filters. Test the unit supply fan and adjust flow to be a little bit higher than you need. If it's a constant volume fan and you don't have a choice for that, turn it on and find out where you're at. Do a pitot if you have to, or do a fan curve to figure out where it's at. Balance all the grill dampers to set the flow. So then you go out and you balance the grills. And then you want to make sure that we know what the total flow is when we're done. And then you verify the totals are close according to, so in other words, you've gone and balanced all the grills, and you have them at design flow, and you have your sheets, and you have the totals of that. And then you come back to the unit and you pitot it, or look at the fan curve to see if they're close. The airflow at the unit should always be larger than the airflow of the grills. And the reason is because we have duct leakage. Every duct leaks. You just want them leaking a lot. So if you have a 2% difference, oh, you're good. You're great to go. If you have a 20% difference, you have a problem. You need to figure out whether it's your pitot is a problem, or whether we have a big hole in the duct somewhere. So that you need to figure out. Balance the water valve to set the water flow. Record the final data, which would be the unit manufacturer, model number, serial number, unit capacity, fan type, number, fan size, RPM, shift data, bore, pitch, diameter, belt, type and length, and fan motor center line distance. Now you're recording all that data for your forms as required by your specification. Fan motor manufacturer, horsepower, motor frame service factor, and motor RPM, voltage, amps, shift size, bore, and pitch diameter. All this data is used by the owner in their maintenance management system, so they'll know what equipment what material this unit has, and what they need to have for maintenance on the system. So that's your job, to collect that data, but you need to make sure you're doing what the specification requires. You don't want to do more, but you don't want to do less to get gigged on it later on. Test the final data, total airflow, fan leaving air pressure of the unit. So you do a pressure profile to make sure you know. There's two things you need. You need to take a pressure profile across this fan. So you have a leaving pressure and an entering pressure. So now you can look at the curve and make determinations of the curve. And then you need to have an external static. What is the pressure of the unit and the inlet of the pressure? So you have total external pressure. Cooling coil, water flow, and inlet and outlet air temperature of the cooling coil. It's not a cooling coil, it's a heating coil. Across the coil. Test and record final unit electrical data, which is motor speed, setting or RPM, voltage and amps, and brake horsepower. Record all grill and registered final balance flows. So, that seems like a lot of work for a little bitty fan, but if it has a duct system with the grills, these are the things you need to do to meet your specification. So heating ventilating units are really simple, and some of them don't have ducts on them, don't have grills. So you just go to the unit, either check the fan curve or test the flow coming out of the supply, and you're done. You still have to record all the data, but you don't have much balance to do. Now, recently, one of the ways we found to be easiest is in the field, is take your mobile phone and take a picture of the motor data and the fan data. So you don't have to manually write any of this down. You can take a picture, save the picture, and you have that data. So in the office, you can put it on your form. All right, fan coil unit. This is a 2-pipe chill water fan coil. So here's the fan coil. We have a chill water coil. We have an electric heater. We have a motor starter to start the motor, and we have an outside air damper actuator. Now, why would you say would you need that? Well, because of the sequence. So the control system has to do what the sequence is doing. So here's the sequence for this. It's pretty simple. Fan shall be on and the outside air damper open when the scheduled in the occupied mode. And that's why we need an actuator on it, because it needs to be off when the unit's off so it doesn't let outside air infiltrate the building. And it needs to be at its balance position when it's on. Modulate the chill water control. So this is not an off-on valve. This is a modulation valve to maintain the temperature and stage the heat strip to maintain the temperature. Monitor supply air temperature fan status. So that's the sequence. It's an easy sequence. Now let's talk about the balance. So of course, 100 grills open, filters installed, test the unit to make sure it works. Now that's part of the tab testing process. You need to test the unit to make sure it works. And that includes the electric heater. You're going to turn the electric heater on and make sure the element actually heats air. It's really embarrassing when you turn in a report that everything works and you find out this heat strip's got a blown fuse and it doesn't work at all. Well, you tested it. No, you need to make sure it actually works. Balance outside airflow. So balance all air grill dampers to set the flow. So you're going to go out here in the duct system like before. And you're going to balance the airflows, and then you're going to balance the outside airflow, this one, to the required outside air. Now, the engineer will probably give you a CFM for minimum outside air requirements, and you need to set that up to that, and then you need to check building pressure, room pressure. And if that pressure is not adequate, you may need to increase this outside air to give you at least neutral pressure, 0, or desired is 0.015. At least 0.015. Yeah, but 0 is acceptable, but minus is not. So if you have negative air, you have to increase this. And that's the reason for that is some engineers don't calculate building leakage, and buildings leak just like ducts leak. And if they didn't account for that, then it means you're going to have a negative building. So you need to do that. Measure the total unit flow by duct pitot, so that, and we're going to compare that to the field, the total of all the grills. We're going to make sure our total flow is according to the grills. And this total flow, there's several things you can use. You can use a pitot as the preferred method, but if there's no place to take a pitot that's good, you may need to depend on something else. And you can depend on a fan curve, take a pressure reading across the fan, supply to return, don't include filters or anything, it has to be just the fan, and read the fan curve, and that's acceptable. However, that's not the most accurate way. Pitot is much more accurate than that. Or you can take a pressure drop across a clean coil. If you have coil data from the Smithel, it tells you what the pressure drop at design flow is, and you could get it from there. Pitot is desired, but if you can't do a pitot, you have to do something else. You have to get somewhere else. And we're trying to verify that the total grill equals the total unit flow, vice versa. Balance the chill water valve to set the water flow. Record the final data. Same data before, all the unit pan, the fan type, all that same data, and motor data. Test and record the final unit data, unit flow, and you also test the heater, which I talked about. So this is the same thing, fan leaving air pressure and inlet air pressure. So we have that right across the fan for the fan curve. Cooling coil pressure drop, we're going to have a cooling coil pressure drop and a filter pressure drop. And this would be at clean filters. And then the cooling coil water flow and inlet and outlet air temperature at the cooling coil. Now, some standards don't require temperature across the coil. The reason for that is it doesn't matter to balance much what the temperature actually is. And the reason is because temperature across the coil has all kinds of conditions that change it. So it could be that the system has absolutely no load, and so the temperature difference may not be great, or it may be that it has a whole lot of load and be really great. Well, that data is not, the reason is because you can't set the load in the building. It is whatever it is. You can't. You could bring in a heater and heat up the space design flow, but that's a whole lot of work, and that's not in your scope to do. So temperatures to me were just that the cooling coil is actually working. It's doing something. How much it's doing is not critical. Test electric heat coil and record total kW voltage in amps. Record inlet and leaving air temperature. This one, leaving and exiting temperature, does tell you something. Because you have a certain temperature of air entering, you have a certain kW going in, and you should have a certain temperature going out. So that's really simple, but not so much here. It is, you can compare the temperature difference to the chill water temperature difference. That is a mathematical calculation. We can do that. By the way, some balancers that have low ethics, I've seen them try to use this one to tell them that they balance the chill water and this is what it is, or vice versa. But if an engineer knows what he's doing and he looks at the report, he can tell you faked it. And the reason is because it's very difficult to take these readings and these readings in an instant in time. For it mathematically to come together, it has to be instantaneous. In other words, you can't take a reading on a coil and wait 5 minutes and take a reading of water. They won't be the same. So you can try to push that kind of stuff, but it doesn't really work if you know what you're looking at. Then test the unit electrical, motor speed, setting and RPM, voltage, amps, and brake horsepower. Now remember, when you're taking voltage, it's the actual voltage per phase and the actual amps per phase. Don't just list it's at 480 or 120 volts or 240 volts or 208. You need the actual readings. Record all grill and register final balance flows. And so that's how you do that. Now here's a similar fan coil, but it's called a 4-pipe. The other one was a 2-pipe. And of course, it should be obvious why they're called that, right? So the last one we did was a 2-pipe fan coil because it had 2 pipes. This is called a 4-pipe because it has 4-pipe. That's pretty simple. However, you need to understand that the definition of 4-pipe is more than 2-pipe, not actually 4 pipes. Because you could have a system with four coils, and then you would have 8-pipe, but it's not called an 8-pipe. It's called a 4-pipe unit. So just that little interesting thing there. Of course, it has a control system that does everything. It's going to modulate both these valves. It's going to turn on and off the fan. It's going to turn on and off that damper. So the sequence again is the fan will be on and the damper open when we're in occupied mode. Modulate the control valves, maintain room temperature, and monitor supplier temperature status. So this control system is really easy for this system. Okay, tab procedure. Obviously, grills are open, filters are clean. Test the supply fan and adjust flow to 10% higher. Make sure I've always used 10% higher just to make it easy in the field. So when I start backing up pressure, I still have enough flow. You may, if you don't do that, you can come back later and change it. Now, about the suggestion I have of balancing systems, these are the preferred method to balance, but not the only way. You could do these in slightly different order. It just might take a little more time totally to do that. But in the end of the day, all the procedures need to be done one way or the other. But, you may have a difference of opinion. But at the end of the day, this is physics. It's not opinion. Balance all grilled dampers and set the flow. Balance outside airflow and mark the adjusted maximum damper position. So you know where that's going to be when it's open. Normally we do that limitation by limiting the stroke of the actuator. So if it needs to be 30% open for occupied and fully closed, we set that linkage that way. Sometimes you might have a damper that needs to modulate for CO2 control or something like that, which I didn't show on this one. So you may not have a set, but you can't do it in linkage, but you may have to do it in software. Measure total unit flow by duct pitot. Verify the totals are close again, so you test your duct leakage. Balance chill water and hot water valves and set the water flows. Record unit data, same thing, all that unit data. And then we're going to test and record the final data. The unit data flows outside air. Remember that outside air again, you set up by the ventilation requirement from the engineer, and then you check building pressure. And if it has a negative pressure, you're going to raise that up to at least neutral. If you have a lot of capacity, I would raise it to 0.015. That's not a lot of air to do that, but we need that pressure. So then you cooling coil and heating coil, water flow and inlet and outlet temperature again. Test and record final unit electrical data, motor speed and RPM, voltage, and record all grills data. Record all grills and register final balance flows. So constant volume system, pretty easy actually to do. 2-pipe constant volume air handling unit. So now we call this other one a fan coil unit. Now normally fan coil units are 2,000 CFM and less, and they might call them blower coils if they get bigger. But the difference between an air handler and a fan coil unit is size and complexity. So this is a full air handling unit. It has a full economizer. So you can see it has a return fan. It has a return damper. It has a relief damper, and it has a inlet damper, outside air damper. So what this is designed to do is this return fan sucks the air from the building, and this is taking all the pressure loss here. It's taking it in this fan, and it takes the air and runs it through the filters and to the supply fan. And if you have an economizer, what this is, so when we're in economizer mode, this damper closes, this one opens, and this one opens. So then we take the air from the building is pushed out by this return fan, and this supply fan sucks in the air from this air. And the reason that's important is because it has a balance component to it. So when you balance a job that's got economizers, you need to balance it both in normal. You need to balance the air handler itself, not the grills, but the air handler itself in both normal mode and economizer mode, because the pressure differentials can change. So we'll talk about that in a little bit. So then we have a chill water coil on this, and we have a heat strip. So this has got a 2-pipe, so it only has 2 pipes. It's got starters on both fans, and it's got a room sensor. Okay, so it's pretty easy. It's got damper actuators on these dampers, and depending on the sequence, these might be modulated or they might be 2-position. And depending on what they are, it changes how you balance the system. So the typical sequence is supply fan and return fan shall run any times the system is in the occupied mode, and the outside damper shall open to minimum position. So again, when we start this unit up, these fans shall run and this damper shall open to that minimum position to get the outside air in. Now, when you look at these systems, if these are big, this is a big air handling unit, this damper might leak enough for minimum outside air. I'm serious. If it's a 5-foot long, 3-foot wide louver automatic damper, it leaks quite a bit, actually, because they call them low leak dampers, but that's in comparison to a damper you can almost see through. So low leak is not that low, so you still have to look at that. Modulate the chill water valve and stage electric heater to maintain room temperature. If the outside air temperature, okay, here's the economizer. If the outside air temperature is between 45 and 70, and the outside temperature is 10 degrees below the return air temperature, enter economizer mode and modulate the outside air and relief and return air dampers to maintain the room temperature set point. If the room temperature rises more than 2 degrees above set point, return to normal mode. So we're going to use this economizer to cool the room during those conditions. So we modulate these. So what happens is this return fan is constant volume, it's running, and so this damper is modulating between these 2 dampers to either put the air here or put the air outside the building and bring in more air. So it's basically maintaining the temperature by modulating that outside air. Monitor the room temperature, supply, return air, and fan status. So basically it's a pretty simple control system. And the only problem for us as tab guys is the economizer. So here's a tab of a 2-pipe unit. Okay, 100% open dampers, clean filters installed. Test and supply the equipment. Does it all run? Now we've alluded to it, but we talked about it a little bit. Why I like to not balance the system until I have chilled water, and if it's a 4-pipe, hot water. And because you don't really need it to do air balance, right? You can do air balance without temperature in the coil, but the problem is I want to finish everything while I'm at that air handler. I want to balance the flows to the water coils. I want to do my temperature readings, pressure readings, and get out of there. If you don't do that, if you come in early to do it, which you might have to do because of schedule, then you got to come back. And remobilization costs money. So I try to have everything there for productivity. Okay, so you're testing everything that it actually works. Balance all air handler grill dampers to set the supply flow. Same old thing. Test the return fan and adjust the flow to provide the neutral pressure at the return damper. So the return air and supply air fans running. No air is relieved or entered from the relief of the outside air. Okay. This is really, really important, and it's done wrong a lot of times. So you have a supply fan and a return fan. So you have to balance and set these up so that this fan is doing a certain RPM, a certain CFM. This fan needs to be doing less than the difference is the outside air requirement. So if this fan is doing 10,000 CFM and you need 2,000 CFM of outside air, this one should be doing 8,000 CFM. And the reason is if you don't do that, and an easy way to tell what's going on is this needs to be, this plenum chamber right here needs to be under negative pressure. This plenum right here needs to be under positive pressure. And this damper right here needs to be right there at 0 somewhere. And the deal is we need this to have outside air. If you have this fan pushing too much air, this is going to be positive pressure, and this becomes positive pressure, then this is not going to be outside air. This is going to be relief damper. So if this is positive pressure, it's going to be relieving air. It needs to be negative pressure, so this sucks in pressure. If this is a negative pressure, so if this has way too little air, and this fan is overpowering, this fan is sucking air out of here, this is now an outside air damper. So if you don't have this set up correctly for these pressures, these two are either relief dampers or they're outside air dampers. And that's a problem. So what you do is you balance this system so there's a neutral pressure right here. So this fan is just doing what it needs to get the air through this damper. So it's taking this air through that and it's placing it there. This should be 0. So this fan should be inducing the negative pressure. This fan should be inducing the positive pressure that's required here. Now, normally buildings, no matter how the designer designs it, don't require relief unless they're in economizer mode. So I have seen many designs where the engineer interpreted the building as a balloon. That this building is not going to leak, so we're going to need to relieve air because we're bringing outside air in for the people to breathe, and we need to relieve that air. Well, it doesn't work that way because the buildings leak a lot, and normally we leak more than the ventilation requirement. So basically, this fan should not be relieving except in economizer, which we'll talk about in a second. So in normal mode, this should be 0 pressure. And I've actually controlled these designs before by putting a pressure sensor across this damper and have it controlled to 0. So you can't do that. So this is kind of the process for balancing that. So this is normal operation. So normal operation, this fan should be lower than this fan by the amount of outside air we need, which would guarantee this be a negative pressure. And then this fan should be adjusted so this is maybe neutral pressure, because if we don't want it to relieve any, very slightly positive but neutral. And because this fan is just taking up all the pressure loss of the return system, and its work is to stop right here. And this fan's work is to start right here and go this direction. So that's the way you need to balance those to be correctly. Balance the outside airflow by changing the speed of the return fan and changing the normal operating position of the outside air damper in software. Mark the new damper position. And remember, this is a modulating damper, so you're going to have to do this in software. You can't do this with linkage. And the reason is because the sequence said when it's not in operation, that damper needs to be closed. So you can't adjust linkage. That needs to be done in software. Verify total building static pressure at the entrance door. Adjust the outside airflow until the building has a slightly positive pressure. So if you've got the total ventilation area you need by the design, then you need to go check building pressure. If it's negative, you need to increase this ventilation air until you have a slightly positive building. Measure the total flow by the duct pitot. Verify totals are close from your grills and registers that you've run out here in balance. And again, you're checking for excessive duct leakage. What you should only be a few percent, 5%, that's okay. Even 10% is okay. But you get past that, it starts getting concerned. You get up to 20%, and they have to fix that. Balance chill water valve to set the water flow. Retest the unit to 100% economizer mode. Okay, here we have to test this again. Open the outside air damper 100% and adjust relief damper position to maintain building pressure set point. So when we get into economizer, it's going to open this damper 100%, and then it needs to be able to adjust this damper to maintain building pressure. So when we're at 100%, so this fan's doing this economizer 100%, it's constant volume, remember. This fan's constant volume, it's on, which means this damper will be closed. This damper will be open, so this is pushing air out. And this is open, so it's sucking air in, and we're cooling the building with this outside air. But during that condition, we need to have the same building pressure we had in normal operation. So what we're having them do is adjust this damper down when we're in economizer mode. Now, if this has automatic control for building pressure, and let me go check. I can't remember what this had. I don't remember. Okay, let's look at the control system here. All right, this one does not have building pressure automated in it. So this one, we're going to test in economizer mode, and we don't have automatic control of the room. If we had automatic control of the room, it could modulate this damper to maintain building pressure, but it doesn't. So you're going to have to set this damper up so when this fan's on, the economizer, this damper's closed, and this damper's full open, you need to adjust this linkage down to where, or in software, adjust it so with that, it needs to have a setting to maintain building pressure. It's very irritating to have a system that changes building pressure during economizer load and blows the doors open. So it needs to be the same building pressure you had during normal operating pressure. Record the final data, the unit data, supply fan, return fan, all that stuff. Test and record the final data, which is the unit total flow, outside airflow, relief airflow, and return airflow. Record building pressure and outside air plenum pressure, both normal and economizer operations. So I would like to see you record the unit pressure profile for both normal operation and economizer operation. The reason is that's going to prove to the engineer you actually tested an economizer. Some guys don't do that. They do normal flow and just ignore the economizer. But you need to not do that because it needs to be tested in both. Supply fan and return fan, leaving air pressure and inlet pressure. Cooling coil air pressure drops, filter pressure drops. Cooling coil water flow and inlet outlet temperature of the cooling coil. Test the electric heating coil and make sure it works and test its record the kW voltage and amps. On some reports, what we've done, which was helpful on a large air handler, is we've actually done a pressure profile, and we actually put a drawing on the drawing, and we list the inlet pressure, this plenum pressure, this plenum pressure, this pressure, this pressure, and this pressure. So the engineer can see the pressure profile as it moves through the unit, and that way he can back check to make sure that the coil that he specified has the right pressure drop and the filter the right pressure drop. It gives him a comfort level of being able to see where these pressures are. You always record the pressure drops, but sometimes it's easier to see it in graphic form than it is in numeric form. Test and record all the final data, the unit flows. Record building pressure and outside air plenum pressure for both normal and economizer operation. Record the outside air relief and return air damper positions for both normal and economizer operations. And the reason we list in the report where those actuators were actually set for, or where we've adjusted the linkage, is so that if something changes in the future, they always know where to get back to your balance condition. Supply fan and return fan, leaving in pressure and inlet pressure. Cooling coil pressure drop, filter drop. Cooling coil water flow and inlet outlet air temperature of the cooling coil. Test electrical heating coil and record total kW, voltage and amps. Record inlet and leaving air temperature. Test the unit electrical data, record all that data, and record your final readings of final flow data. Now sometimes when you balance a big system, of course, you have preliminary readings that you run out and take those readings, and then you do a proportional balance, so then you have a final reading. And sometimes the final reading you do is low. So you've done a proportional balance and you're 10% low on flow or 15% low on flow. Then you come back to the unit, speed it up, and what you need to do is make sure you have in your balance report, you have the preliminary flow and the actual final flows, and those final flows match the unit final flows. So you may balance everything, have to come back and trim things off when you've got things up to where they need to be. Okay, here's a 4-pipe constant volume unit. Now it's got a chill water coil and a heating coil and a pre-cool coil, a preheating coil. So now this has got 6 pipes, still a 4-pipe unit, okay, still the same thing. It's got a control system. This one, again, does not have a building pressure, but it's got a supply air temperature. It's got dampers, auto dampers. It's got starters for the fans, and it's got modulating valves. Typical control sequence: supply fan, return fan on, the outside damper at minimum position. Modulate the preheat hot water valve to maintain the, okay, we're going to do a preheat sequence. So modulate the preheat hot water valve to maintain the preheat set point temperature of 45 degrees measured at the leaving side of the cooling coil. So you realize that 45 degrees may be the set point of the cooling coil. So we're going to turn off the heating coil. If it gets above 45 degrees, the heating coil goes off, the preheat coil. This is designed for a cold country where it might be, minus 10 outside, and you're bringing some outside air in that's made the inlet air too cold. So this preheat coil is preheating things up. If it senses, this sensor right here, this is a sensor that passes cooling coil. If it senses air below 40 degrees, it's going to do a freeze. If cooling coil drops below 38 degrees, we're going to stop this air handler and issue an alarm, and we're going to open these water valves. And what we're doing is trying to prevent them from freezing. So it does mean we turn the unit off so the heating stops in the building. We're not going to freeze up the coils because we've stopped it. And we've turned the water on full, so the hot water turns on and the chill water turns on. This hot water turns on to keep these coils from freezing. Modulate the chill water valve and hot water valve to maintain room temperature set point. If the outside air, okay, here's our economizer sequence, which is the same as before. It gets cold outside, then we turn on the economizer. Now here we have a humidity override on this one. Because we have a heating coil downstream, we can actually dehumidify with this unit. So if the room humidity rises above 60%, place the cooling coil into the dehumidification mode. When the room humidity drops below 45%, return to normal temperature mode. In dehumidification mode, the chill water valve is to maintain the cooling coil leaving temperature to maintain a 50% room humidity, and modulate the hot water valve to maintain the temperatures. What happens is we drop the temperature on the cooling coil beyond what we want for the room, and we start dropping. Now, some sequences just open this valve 100%. Well, I don't like doing that because then we reheat it, so it's not energy efficient. So what I do is I actually run this cooling coil to 50% room humidity. So it will open 100% full and reheat the air so the temperature doesn't get too cold until we get to 50%, and then it will start modulating this chill water valve to maintain 50%. If the room drops below 45%, then we're going to turn off the dehumidification mode and just go back to cooling mode. Monitor room temperature, supply the return air. So now let's talk balance. Same thing. 100% on grills. Verify new clean filters. Test the unit fan, adjust flow to plus 10%. Make sure everything works. Balance and supply our grill dampers and set the flows by proportional balance or by any means you do out there, so you balance all these grills. Now, some of these units can be quite large. This might be 20,000 CFM. It can be a very big unit with very large zone. So like this could be an auditorium. It'd have one zone and have a lot of air. So basically, this could be a very big unit. Test the return fan and adjust fan flow to apply the neutral pressure at the return air damper. That neutral pressure again, so remember, the air is coming in here, it's not relieving, it goes through here, it becomes negative to pull in outside air, it goes to this fan. This is really where the talent comes into balancing an air handler, is if you can get zero pressure there, you're doing a good job. Just to let you know, this is what's important. Balance the outside airflow by changing the speed of the return fan and changing the normal operating position of the outside air damper in software. Mark the damper maximum position. Verify the total building static pressure at the entrance door. Adjust the outside air until we have a slightly positive building. Same procedure for all economizers. Measure total flow by duct pitot. Verify the totals are close. So make sure that what you've measured at the grills is close to the unit flow that you have here. If it's greater than 15%, 20%, you got a problem. Balance chill water, hot water, preheat valves, and set the water flow to design. Retest the unit in 100% economizer mode. Open the outside air damper 100% and adjust the relief damper position. Maintain building pressure set point. Same thing for economizers. Record all the unit data as you would before. Test and record final data, which is going to be the unit total flow, outside air flow, relief flow, and return air flow. Record building pressure and outside air plenum pressure of both normal and economizer operation. Record outside air, relief, and return air damper positions for both normal and economizer operations. supply fan and return fan, leaving air pressure and limit air pressure, cooling coil, air pressure drop, filter pressure drop. And balance cooling coil water flow and record inlet and outlet temperatures of cooling coil and balance water flow. Balance heating and coil and preheat coil water flow and record inlet and outlet air temperature of the coils at balanced water flow. Test and balance the unit electrical data, take those electrical readings and record everything in your report. Okay, now this is a different beast. This is called a dual duct air handling unit. And the reason is it has a heating deck and a cold deck. So it's got these two plenums. One's a hot air, one's a cold air, and then it has duct systems that go through the building. Two ducts. It has a cold duct and it has a hot duct. And then you have these boxes down here for the room. And these are actually constant volume. Because what happens is this is a constant volume fan. And these are either, in the old days, these had one actuator, normally a pneumatic actuator, on one shaft. So when one's open, one's closed. So you always had constant volume because it's either coming from the hot side or the cold side or some mixture in between. And the room temperature sensor is actually adjusting that damper for temperature. And it's blending air from the hot side to the cold side or cold side to the hot side. And this was a way for us to have variable temperature in the space with a constant temperature system. And that's what these are for. Now, that's the good news. These work really, really well. The bad news, they're expensive because you're running two duct systems, and they're full flow duct systems because this one, it depends. If you were in a hot climate, this duct would be 100% of this air handler can flow down this duct. And maybe you never needed that much air for heating, so this would be a maybe slightly smaller duct. Or vice versa, the heating system, this would be full flow, and this may not be quite full flow duct system. Part of the design, but that's the way it does. The control system is a little more complicated because it has heating coil, cooling coil, still has an economizer dampers, and it has fans. And then we have thermostats in the room to run these dampers. Now we'll go over and look at this a little bit. This is what a modern one looks like. So we actually have two VAV boxes, that's what they are. But they have a common sensor downstream, so they're a constant volume. Both these will modulate. So this is a modern version, and normally these are just two VAV boxes, but they have special routine software in here to make them a dual duct constant volume system. And we have a pitot port grid that's downstream instead of upstream like normal. So the downstream keeps them constant volume. So these will modulate to temperature in the space, but this velocitrol never lets them get below or above flow, makes them constant volume. So the dual variable volume box controlled by downstream flow varies the flow between cold deck and hot deck to control room temperature. The velocitrol provides constant flow to the room. Second box is slave to the first box, and normally the heating box is slave to the cooling box, unless this is in a very cold place, so the heating is going to be a denominator system. Supply air is constant volume, variable temperature. So basically, to the room is constant volume, variable temperature, whereas this system is constant volume also. Actually, that flows down these ducts are variable volume, but don't confuse it. This is constant volume. This is constant volume. Room temperature sensor modulates both the hot deck and cold deck terminal without unit dampers to provide room temperature. The cold deck box acts as the lead box, and the hot deck box is slave to the cold deck box. The reason we talk about that here is most systems are for, this kind of system would be in office buildings or schools, and indoor heat load is always going to be there. So your probably predominant is always cooling. And also you need to think about ventilation air. And normally we have the cooling side be where the ventilation air, so we'd have a minimum position on the cooling valve. So we'd always have some air for ventilation in the space. The supply and return air fan shall run in the outside air damper should be minimum position. Anytime the system is in the occupied mode, modulate the chill water valve to maintain the cold deck temperatures. We have a temperature sensor here and a temperature sensor here. This valve modulates to maintain that temperature. This valve modulates to maintain that temperature. Reset the cold and hot deck temperature set points based on terminal box load or damper position. Cold deck reset range should be 54 to 75. Hot deck range should be from 75 to 120. Energy efficiency is maximized by resetting the hot deck to as close to the return air temperature as possible. When these first came out years ago, and this is before my time when these first came out, is they actually ran this at 45 degrees and this at 120 degrees. Because energy didn't matter much back then, and they just ran them that way. Well, when I finally came into the picture, we were now economizing these. So when we do a retrofit on one, we would try to make this temperature return air temperature. So now we're taking the heat of the lights and the heat of the space, and we're using that air to trim off building when it didn't need much heat. So like during the summertime when one area got a little too cold, or during the autumn, or during the mid-seasons, we could use return air, and we became energy efficient that way. So that's what we're trying to do. So we're watching what's happening down here. If these dampers need more cold air, then what we do, but not more air. If they need it colder, then we start lowering the temperature of the cold deck. If they need it hotter, we start raising the temperature of the hot deck. But we always start with this at 45 degrees and this at 80 degrees to see if we can make them work that way. And this is the economizer. Won't go through that sequence. Monitor the room temperature. So now we're going to talk about balance. Guess what the first item is? Right. All dampers 100% open. Filters are clean and installed. Testing the unit to make sure it works. Set the terminal unit to full cooling. Set all terminal units to full cooling and balance the supply air grill dampers. Calibrate the box controlling the full flow to all the grills. Now, you don't actually have to do this. You can let it just be wherever it's going to be for temperature and balance it, because flow is constant. It's a constant volume device. However, in these newer systems, we don't have pneumatic actuators. We have boxes. You got to calibrate the box. You still have to calibrate the box. So there is a procedure to do that. I normally do cooling coil first, cooling side first at 100% flow, and calibrate all those cooling boxes, and then calibrate the heating box for maximum heating flow in case the engineer has it different. So if the cooling coil and the heating coil are the same flow, then you can calibrate them the same. If not, then you're going to have to do full heating flow, whatever that is, and then calibrate the heating side boxes. So it's something I can't say here because the field conditions will dictate it. But normally doing one or the other is the way I do it. Test and return the fan and adjust the fan flow to provide neutral pressure at the return damper. Here's our magic happening at the economizer. Balance the outside airflow by changing the speed of the return fan and change the normal operating pressure of the outside air damper in software market. So what we're doing again is getting these balanced, so we've got a neutral negative pressure to get our outside air, and then verify the building pressure by adjusting how much outside air we got coming to the building. Yeah, so you had all the dampers locked in their open position, so now you can't do this. Remember, this is a constant volume system, no diversity, so you locked all the dampers open to do the cooling side, and now we're releasing those, measure the total flow by duct pitos, verify totals are close, again for duct leakage, balance the coils, retest the unit 100% economizer, record final data, all the unit data, test and record unit data, which is all the pressures and flows like we do anywhere else. Supply and return fan, all its inlets. You're going to do pressure profiles across the fans. And we're going to do pressure drops across the filters and pressure drop across each coil. Balance cooling coil water flow and record inlet data. And you're going to do the hot water coil also. Test and record all electrical data like you would any other unit. And then record flows of the terminal unit. So now we have another kind of unit that mimics a variable volume flow, and it's called a multi-zone. And what this does, this air handler has the same looking air handler supply fan, and it blows through a cooling cold deck and a heating hot deck, just like the dual duct system, except it's dual duct for about a foot. And then it goes to a constant volume. It has a damper. It has dampers discharge per zone. So if you have 4 zones, you'll have 4 dampers, 4 heating dampers and 4 cooling dampers. And these are on a common shaft. So if the cooling damper's open, the heating damper's closed. And these actuators up here are actually the zone dampers, control dampers. So instead of having VAV boxes, you got these dampers right here at the unit. So if you had 4 zones, I think that shows 3 zones, then you'd have 3 thermostats in the rooms controlling these 3 actuators. And so the air comes through, it goes through the cold deck, and this damper adjusts its flow, goes through here to the heating deck, and the damper adjusts the flow. Now this, I just kind of alert you to this little dotted line here. That's actually a blast gate. So when the air blows out of this air handling, this fan, it's a jet, and it'll jet right through this cooling coil, and it'll stratify the temperature through that coil because it has this jet, high velocity jet. So this blast gate is here to give some back pressure to break this air up and force it up to this plenum and around this plenum, so we get even flow across the cooling coil and the heating coil. So that's it's actually a blank plate with holes in it. So it's just a blast gate. We have our 2 coil, 4 pipes. We got pipes to the hot water and pipes to the chill water. Got a control system. Now, these are the 3 room sensors out there that do these 3 dampers. Everything else is like the air handlers before. Sequence is the same. Both fans should be on. The outside damper should be at minimum flow when it's occupied. Modulate chill water valve to maintain this deck temperature. Measure the hot water valve to maintain this deck temperature. And we do the exact same thing that we did with the dual duct. We maintain this at about 45 degrees to start with. And then we will have the hot deck, and we'll try to reset this at return air temperature to start, so that we're trying to use the heat of the lights and the heat of the load of the building to provide reheat into the space when we need it. Room temperature essentials should modulate the multi-zone damper that mixes flow cold and hot decks to provide room temperature control. Then here's the economizer, which is exactly the same temperature as the other one, or sequence of the other one, for the economizer load. Now, one thing about economizers, show you here, the multi-zones, and the reason these are not too popular now, I still see them every once in a while when we have really large zones. Say you have a zone that's 5,000, 8,000 CFM. They don't make 8,000 CFM boxes, so you'd have to use several boxes to hook together, and that's just not seeable. So they will actually do large zones, like I did a Disney attraction, Star Wars attraction at Disneyland, and we had these huge multi-zones because we're cooling the zones around all that park ride, and that, it might be 10,000 CFM in one zone and 4,000 another, 5,000 another, and they use a multi-zone. The reason they don't use it normally is because they're expensive, because you're running a full-size duct 3 times from this air handler out to each zone. Now, in my early days of doing design, I've had multi-zones with 11 zones. Man, you ought to try to design the duct. 11 zones leaving this unit. Some of your zones were 4 inches, 1 damper wide, so you had 4 inches wide. The way they size these is this actuator may be controlling 3 dampers. So you put on the face of this unit is a whole bunch of dampers, maybe 20 dampers wide. And then for each zone, depending on how much CFM, you link them together. So on one, you may only have 1 damper, the next one you may have 4 dampers, the next one you may have 11 dampers. And they did that just to verify the size of the zones. So cost is a limiting factor in a multi-zone. So balance. There we go. 100% grills open again. Clean filters. Test everything to make sure it works. Set the zone dampers to full cooling and balance all supply air grill and return dampers. So normally use cooling again. Set all these to cooling and go out and balance all the dampers in the field. Now remember, this actually can't have diversity either because it's constant volume unit. Balance flow between the heating and cooling, but it's still constant volume. So there can't be more air out there than there is here. It just can't be. Balance the outside airflow again by changing the speed of the return fan and setting that damper, and then go check to make sure you got building pressure again. Measure the total pitot, make sure it matches somewhat what you measured in cooling flow. Again, it should be larger than what's in cooling flow. One area of problematic duct leaks is that joint between the zones. Right here at those dampers, when you have one zone that includes 4 dampers, one includes 2 dampers, the joint between them is normally only 1 inch wide. It's the flange of your duct. And if there's a leak there, it's really difficult to seal. So those are problematic. And if you have a lot of duct leakage in multi-zone, I would check there first. Balance chill water and hot water coils. Test the unit economizer. Do that same thing as you did before. Record your final data. Unit manufacturer, supply fan, return fan type, all the tag data. Supply return fan motor data and all its tag data. Test the unit and record final data. Unit airflows, pressure, just like you've done on the other units before. Record building pressure and outside pressure, plenum pressure for both normal operation and economizer operations. Supply fan and return fan, leaving air pressure and inlet air pressure, cooling coil and heating coil air pressure drops, and filter pressure drops. Balance cooling coil water flow and record inlet, and same with the heating coil. Test and record the electrical data like you would any other unit. So now let's talk about computer room units. They're a constant volume air handling unit actually. And a computer room unit, a traditional computer room unit, sits on a raised floor and it sucks air in from the top from the room, puts it through a cooling coil, has a humidifier in it, goes a fan and blows it down into this floor plenum. And then in the space, they put floor tiles that have holes in them for louvers, but they're normally just drilled holes. And that allows the pressure under the floor to escape up into the aisles. And the proper way to do this is hot aisle, cold aisle. So these are the computer racks, and they have lots and lots of computer racks. So they make this a cold aisle. So they take and put only the supply louvers in this aisle, and they don't put any over here. So what happens is the fans in these processing units suck air in from this direction and blow it out this direction. So they take the cold air from the cold aisle, run it through the processor to cool them, and exits the other side, which is hot air. So now we have a hot aisle here. So the way I always like to, and then this air goes back to the top of the unit. The way I like to do this in practicality was I put return grills in the ceiling over the hot aisles, not the cold aisles, forcing this air to get through these units or up into here. And then they take the hot air and put it in a return air plenum. And then over these units in the ceiling, I put another grill here to allow the plenum air to come down, or actually we put a duct from here up to the ceiling. So these units were sucking air out of this plenum, which is all this hot air. And this allowed the system to be a lot more efficient. So it's underfloor supply. Racks have cold and hot aisles. Return air can from ceiling or return air plenum. Size is 5 to 25 ton capacity, normal. Temperature and humidity control. These units control temperature and humidity very accurately because the space can't have any high humidity because of static. Electronics don't like static pressure. These all have standalone control systems. And if you want to, you can integrate them to a normal control system, but really all you're doing is monitoring what they're doing. And you can do a set point change in both temperature and humidity, but you don't actually control. The unit controls itself. Available with chill water or DX or combo units. They do have units that have both, so the DX is standby in case the chill water fails. They have standby depending on what's happening in the space. Typical sequence is pretty supply. Supply fan should run anytime the system is enabled. The internal unit control panel should modulate chill water and humidifier to maintain room temperature and humidity set points. Unit can be integrated into the monitoring system through a network integration. Upon receipt of the unit alarm, the unit shall be shut down and alarms shall be sent to operational staff. So in case you have normally the alarms in here, if you have a high humidity alarm or a high temperature alarm, it doesn't actually shut the unit down, it sends an alarm. But we do have leak detectors down here. So if there's any water comes off this unit, it shuts it down immediately. And monitor the supply. So okay, tab balance on these are super simple because there's not much you can do. Test the fan and you say, oh, look what we didn't do. We didn't have to test the grills, right? Because there aren't any, so you don't have to. Test the air and humidifier operation to verify they actually work, and then provide total airflow by measuring the return air. If it has a duct, you take a pitot, otherwise take a Velgrade of the inlet air, and you're done. There's not much. You can verify the grills are in the cold side of the aisles, record the unit return airflow, and unit and amps and temperature and humidity set points, and you're done. So those are pretty easy. Nowadays, talk chill beams. Chill beams. Chill beams are just normally a fan coil unit. Constant volume chill beams have a fan coil unit with heating, cooling, and dehumidification capability. That's really important. So the heating coil has to be downstream of the cooling coil. And then we have these chill beams, which are nothing more than a, I didn't put it in here. It's a cooling coil, actually, in a grill. And it allows as these get, and then they blow air across this cooling coil into the space. And this actually is an induction grill. It actually allows you to induce return air or room air across this coil at the same time this air is going in there. And they're called chill beams. And it's kind of interesting how these happened. Originally we had chill ceilings. The reason they were called chill beams is that the original intent in Europe was that we had flat aluminum panels with serpentine copper coils on the back, and we ran cold water through those to cool the plate in the ceiling, and that absorbed heat from the space. It's radiant heating backwards, right? It's radiant cooling, so it sucks it up instead of putting it out. Well, some spaces they didn't have enough space, so they built a box beam and put it in the space, and they put chill ceiling panels on all three sides of the box beam, or some cases all four sides, if it was exposed in the space. And they called it a chill beam, because it was actually a beam surrounded by panels. Well, what happened is we started doing chill ceilings many times, and the intent was to have the ceilings take the sensible load out of the space. And then the outside air would bring in and take care of the latent load in the space. Well, many times we didn't have enough space in the ceiling, because there's sprinkler fittings and light fixtures and things in the ceiling. So we couldn't do the whole ceiling, and so we a lot of times ended up with not quite enough panel space to do the total sensible load. So some bright individual, I don't know who, came up with, well, let's take these and put cooling coils in these because they have a whole bunch of surface area. So with a chill beam, what's called a chill beam today, is actually allows you to do the same thing as a flat ceiling did, except we have a whole bunch more surface area in these chill beams. Okay, history lesson for you here. The fan coil unit shall run and the outside air damper shall be open anytime the system is in the occupied mode. Modulate the chill beam chill water valve to maintain the room temperature. The chill beam chill water supply shall be controlled to 1 degree above room dew point temperature to prevent condensation. This is really important. So what it does is this water that's running around into these chill beams is kept at a temperature that will not condense. So these will never condense. And it's a real simple sensor. It works, but you read humidity and temperature and calculate dew point, and then you keep that temperature above it. Modulate the fan coil chill water hot water valve to maintain supply duct temperature set point. On fan coil start, the supply air temperature set point shall be set to 70 degrees and the reset based upon the room load. Every 5 minutes, pull the room temperature sensors. If any chill beam chill water valve is more than 95% open and the room is more than 2 degrees above set point, decrease the supply air temperature set point 2 degrees. If no chill beam temperature control valve is open or above 60% open and any room is more than 2 degrees below set point, increase the supply air temperature set point 1 degree. Reset range 58 to 85. Okay. These sequences can be all over the map. This just happens to be a job I did, and I just took that sequence to actually look at it. But they can be all kinds of different complicated sequences like that. If the room humidity rises above 60%, begin the dehumidification mode by controlling the fan coil unit chill water valve to 55 degrees. As measured at the mixed air leaving temperature sensor, modulate the chill water valve to maintain 50% room humidity. Modulate the hot water valve to maintain the supply air temperature set point. The room humidity drops below 48% in the dehumidification mode. Monitor the room temperature, room humidity, and supply air temperature, supply air fan status. Alarm if the room humidity rises above 65%. We do not want this system to condense. So that's why it's really important to keep the room below 50%, 50% or below, and really, really important to keep this pipe temperature, water temperature, below dew point of the room. Okay, tabbing this system. This has been somewhat controversial, and I'll go why. Okay, so verify all duct dampers are 100% open. Okay, make sure these are all open. Test the fan coil unit, make sure it all works. Measure unit airflow by duct pitot. Adjust balance valves to set the control of water flow. You notice I haven't mentioned about doing this yet. Balance the outside airflow to provide minimum ventilation flow, so you're going to balance that. Balance flow to each chill beam to design CFM flow. Okay, here's where it gets tricky. Normally, you utilize a manufacturer's table of pressure drop versus flow. So most manufacturers give you what the pressure inlet should be right here to give the proper flow. And so you normally set this with pressure differential across that. I don't know how accurate it is. It's difficult because it's an induction grill. You're reading primary flow here, not secondary. If you try to take a hood, you're going to read secondary flow, which will include this flow plus the induced flow. That's why you can't measure it that way. That's what's different about these. But they're probably pretty forgiving. If you make a mistake, it's probably not going to be critical. But you set these upon pressure, depending into the manufacturer's data. Balance the chill beam water flows. Record unit airflow, outside airflow, return air and supply airflows. Record chill beam airflows and water flows. Record leaving and entering duct static air pressure for both supply air fan and chill water and hot water coil flows. That's it. So you've gone through constant volume systems. Congratulations. I apologize if I talk too fast, but I didn't want to make this video to be so terribly long to do that. So hopefully this was really helpful to you. That's what I said. You might have to watch this again to catch my quick talking. Sorry about that. Really appreciate you being a subscriber. I really appreciate you watching the videos. I hope they're meaningful to you. Have a great day. Catch you on the next one.